we have seen univariate regression in which the size of the house, the cost of the house is dependent on size of the house. Okay, so here the thing is that you have cost as the dependent variable and size of the house as independent variable. Okay, so this is your x and this is your y. Okay, so this is called as univariate regression because you have only one variable on which the y is dependent. Okay, but now instead of size of house, if I change and have some let's say some other attributes on which the cost of the house is dependent. So for example, I say that now I have size, then number of bedrooms, then location, age. Okay, so these are the four attributes. So this is one, this is two, this is the location is third, then age is fourth, on which the cost is dependent. Now I have four independent variables on which the cost, that is y, that is dependent. Okay, so in this case, now here the regression is multivariate regression. Okay, so now let us see the notations and then the multivariate regression model. Okay, now since the number of attributes have been changed, so here now we will have n is nothing but again the size of the data. Xi is the input feature of ith training example. Okay, so x is the input feature for the ith training example. And now if you put j in the subscript, so the notation changes from the book, resources, literature you refer. Okay, so now here I put it into subscript, so value of feature j in ith training example. So how many features are there? There may be say d features. So I will put the feature number in subscript and the sample number in the superscript. Okay, so like that. Now what is my hypothesis? Or hypothesis will become, so I will have y cap of x I is equal to theta 0 into theta 1 into x1 plus theta 2 into x2 plus then up to theta k into xk. So I have, let's say, k features. So there will be k coefficients. Okay, now here I have assumed that this will be a multivariate linear regression because I have not put any higher order polynomials on this particular feature value. If you put higher order polynomials here, so it will become a polynomial regression. Okay, so now look at this. Now I say that x is a feature where I have all this. X is a vector where I will have all these features. So I will say x0, x1, x2 up to xk. There is no such x0, but we assume that for theta 0, x0 is equal to 1. Okay, so this will represent a numerical value, obviously. So it will be a subset of the real value. And then theta bar is nothing but a vector having all those parameters, or say the coefficients of this particular multivariate linear regression. So you will have theta 0, theta 1, theta 2 up to theta k, and that obviously will have a real value the real values. Okay, now the hypothesis, now as you can see that y cap is nothing but the multiplication of this. Okay, so theta transpose into x. Okay, so you can either transpose this or this, doesn't matter. So I have transposed that theta bar, that is this vector. So if you put this, if you make the transpose of this, it will be how much? It will be 1 by k, and this is k by 1, so it will be 1. Okay, so it is 1 by 1. So y cap is equal to theta transpose into x. This is what is the general conventions to write this linear regression. Okay, in the vector form. Now, now let us write the model. So hypothesis is y cap is equal to theta transpose into x, and then what is the parameters? Parameters is nothing but theta 0, theta 1 up to theta k. So that is in the form of vector theta cap or theta bar. And the cost function, now again the same thing, the cost function will be to minimize the number of errors. So it will be j theta bar. So here it is to minimize all those, select all those theta 0, theta 1, theta 1 up to theta k, such that the error, sum of the squared error is minimum. So y cap of xi minus y of xi, and this square means this is the error. So you can write it this and this. This first doesn't matter. Actual minus predicted. No, this is predicted minus actual square, and then summation of this, and then taking the average. So it is 1 by 2n. Okay. And what is the objective? Objective is to minimize j theta. Okay. So this is what is a multivariate model of linear regression. Okay. Now if you write it in the form of matrix, okay, look at this, y1 up to yn, then 1 1 1 1 into theta 0, x1 to xn into theta 1, and then epsilon 1 to epsilon 2 in the errors. Okay, so generally in most of the literature they add the epsilon term or the error term in with the linear regression model. So this is y is equal to theta 0 plus x into theta 1. So this is a simple linear regression univariate model. Okay, and then same thing can be applicable to multivariate model. So homogeneous coordinate system can be used to simplify the equation y1 to yn. We have already seen this. So 1 x1 1 x2 1 x3 up to 1 xn, and this is theta 0 theta 1 plus epsilon 1 up to epsilon 2. So ultimately what will happen, this is what is n by 2 and this is 2 by 1. So n by 2 2 by 1, so it will have n by 1, and then you will have all those y1 y2 y3 yi values for every particular this. Okay, so this can be done with the zero-centered value. So we have already done that. So assuming that every feature is zero-centered and has a mean that is 0, and thus x transpose y is an n vector holding all the required covariances. So we have already seen that S is the diagonal matrix with the diagonal entries that they are nothing but the covariance of that particular features. So we can, sorry, the variance of that particular feature. So we can get the required scaling matrix by simply inverting S. Okay, so you can invert S and then you can get the scaling matrix is available. Okay, so the first step to the solution is that for the multivariate regression problem, so you can have theta cap is equal to S inverse into X transpose Y. So finding out the theta 0, theta 1 for univariate model is very easy. But the problem is how to find all those theta 0, theta 1, theta 2, theta up to theta k for the multivariate kind of model. So here the thing is that find the the scatter matrix, invert it, you will have a scaling matrix, then take the inverse of that and multiply it with the X transpose Y, and then ultimately the theta cap can be estimated as X transpose into X inverse into X transpose Y. Okay, so this is what is X transpose X inverse acts as a transformation that decorrelates centers and normalize the features. So this will normalize your features and that ultimately be multiplied with your X transpose Y, and you will get all the estimation of theta 0. So that can be also, you can take one example of multivariate linear regression. You can have all those values and then you can find out or estimate the values of theta. Okay, so this is the way to find out the coefficients for multivariate linear regression. Okay, now we will see what is a regularized regression. Okay, now if you see that if you have various parameters and various features, then the least square method generally becomes unstable and it depends totally on the training data. Okay, and this particular instability will make the model to overfit. Okay, so probably if you have a kind of complex model, so here look at this, if you have 2 points, then a linear model will directly go from this particular 2 points. We want to minimize the error, so we will make it to go through this. If you make the model more complex, so you will have all those curves going to this particular 2 points. Okay, so a linear model will fit with zero error, but if we apply some sort of quadratic model, then changing the settings and some parameters, we can make that quadratic model also with the zero error. But the thing is that they will have overfit, they will be overfitting, and then we can allow this model not to overfit by using regularization, because if you overfit your model, then for the new data points that will be coming, the model is going to give you a high bias. Okay, so how to choose among this model, we can cover this even later, because now I think this is let us have some introduction and then we will cover it in the next session. So we can choose by, there are many approaches, but one way is to choosing the lowest order polynomial. Okay, so if you have a higher, all those terms with the higher order polynomial, you can skip that and you choose the terms that is having the lower order polynomial. So the higher order coefficients can be made to 0. Ultimately, they can be even eliminated. Okay, and another common approach is to make sure that the weight of that particular uh, parameters are small. Okay, so you can have that a small magnitude parameters, and this particular method is called as shrinkage. Okay, you can just consider that small weightage or small weight parameters. Okay, and now if you can write down the LSM or the least square regression problem as theta star is equal to minimum of theta. Okay, I said minimum, though you are selecting the small values uh, parameters. So y minus x theta transpose into y minus x theta. Okay. So y minus x theta transpose is another on this particular y minus x theta transpose into y minus x theta is another way to write sum of the squared method. So we have seen how to write the sum of the squared method is x transpose x inverse into x transpose y. Okay. So this is the way we write the sum of the squared method using the matrix notations. But there is another way to write that. So this is what is another way. So now, how do you optimize this? How do you regularize this? So let us say that theta star is nothing but minimum of theta and those all least square method plus lambda, and then I say theta square. Okay. So where this theta square is nothing but the sum of the squared norm of vector theta. So this is nothing but the sum of the square terms of vector theta. So here you can say theta I square, and then I take the sum of this. So it is actually equal to the dot product of theta transpose into theta. Okay, so it is the dot product of theta transpose into theta, and lambda is nothing but a kind of you say tuning parameter or a regularization parameter that will denote that how much amount of the regularization is required for your particular model. Okay, so for example, if I take 0.1, then in that particular portion the regularization will happen. If I take 0.20, then 0.2, then I can say that that regulation, I will take only the 0.2 of this particular theta, squared norm of this particular theta. Okay, so the regularization can be even this particular squared norm can be also written in this way. So I will not explain this right now, but this is what is very easy to understand. But if you can if you are compatible with the vectors, then it will be very easy to understand. Okay, so lambda is nothing but that you can add the diagonal values of x transpose x. Okay, and that can even make your model more stable. Okay, so lambda can be added to the diagonal values. Diagonal values are nothing but your variance of that particular feature. Okay, so you can add that lambda to those diagonal values, and that will make your model more stable. Okay, so the way what we have discussed right now is nothing but a ridge regression, because now if you can see this, so let's say alpha is equal to 0, and alpha, or here I say lambda is equal to 0. So look at this. This is what is the linear model. Then I have some complex model, then some other complex model. Okay, so this is unregularized version of the regression. Here linear, then this may be say quadratic, this may be higher order polynomial function. So you can see that these lines are going through each and every point. Okay, but if I regularize, like say alpha is equal to 1, then look at this particular linear regression, then this particular quadratic equation, and now this particular complex equation is regularized to this. Okay, now these are almost same. So the thing is that now they are normalized with this, and you can now compare the output. So this is fine, but ultimately the thing is that if some new points are get added, this won't work. Okay, because it have been tuned to fit this particular data points. Okay, but now if you have a regularized version with say lambda is equal to 1, you take only one portion of that particular square norm of that particular theta. So now this is limited to this. Okay, now even if you have even more higher order polynomials, then it will not go beyond than this. Okay, so this is what is the use of regularization. Okay, so if we choose lambda as large, we tend to reduce parameter magnitude than the squared error. So the complexity is of the model is reduced. So we are not bothering about the errors. Okay. So this is about this. Now you can see about the LP regularization. Now this is what is here. We have squared norm. Okay, you can see this is squared norm. Now instead of this, now this is what is the p norms. Okay, so you have theta I raised to p, then sum of that, and we take again the inverse of that. Okay. So this is what is 0.5. So these are the isosurfaces drawn with that. This is called as lasso. Lasso is least absolute shrinkages and the selective operator. Then this is p is equal to 2. You can have it quadratic model. Then p is equal to 4. You can see that the isosurface is drawn as the square. Okay. So you just can think about this as a various regularizer depending on the complexity of your model. Okay. Uh, that's it. Okay, I think we should stop here, because again for the next session I will start with the new topic, or even if you want I can record. And thank you very much for watching this video. If you have liked this video, please click on like button and subscribe to my YouTube channel, and please write your suggestion, queries in the comment box, or mail me at dineshjhende@gmail.com. Thank you very much.